I'm Jason Cain. I'm going to be moderating this panel discussion today. So I'll introduce the other panelists and have just kind of a couple of opening remarks. Gyuszi you met already, and he's given a very nice presentation. I also wanted to introduce Luigi and Maarten. Dr. Luigi Capodieci down there on the end is Chief Technical Officer at Motivo Data Analytics. He's worked in this field and related fields for a long time, and we've worked together for a big chunk of that time. He's worked on lithographic imaging, patterning, and process simulation for more than 20 years. We got to know each other at AMD, where he was working for many years, and he was a pioneer in the field of DFM, and many other related technologies that spun off from that. He went with the Global Foundries when that split happened in 2009, and worked there for several years managing DFM R&D from the 45 nanometer node all the way down sub 28, I believe. In 2016, he left and founded Not Prime, a data analytics startup company, and I believe they are combined with Motivo now. Yes. Okay, they merged with Motivo Data Analytics, where he is CEO. Luigi has a doctorate degree in electrical engineering and computer science from the University of Bologna in Italy, and also a PhD in electrical engineering from University of Wisconsin in Madison. And he has over 40 U.S. patents and is an active member of IEEE and ACM, and also, I believe, a fellow of SPIE. Please welcome Dr. Capodieci. Our other panelist is Maarten Berkens. He is the Chief Technical Officer from Sage Design Automation. He has been working in the field also a long time, and worked on physical design optimization, yield enhancement, and design rule modeling for over 20 years. He spent a long time at Philips Semiconductor, where he worked in non-volatile memory. He joined Sagantec as CTO in 1997. And then Takumi in 2004, where he was a CTO, and then finally over to Sage 2012, where he was a co-founder and Chief Technical Officer. Maarten has a Master of Science in Electrical Engineering from Eindhoven University, and he has numerous patents and publications as well. Please welcome Maarten. All right, so I just wanted to give a little bit of perspective, and this is my opinion, I guess. So I'll be curious to see what our panelists have to say. But I kind of wanted to set the stage by listing a few pattern matching applications as I see them in semiconductors. So this is a partial list, not meant to be an exhaustive list of applications. But I think the one that we've focused on so far today is in design rule checking. That's what Gyuszi devoted most of his talk to. So I think that can kind of be subcategorized into two classes. One is restrictive design rules, which are kind of conventional design rule checking. So those are forbidden patterns or forbidden layout constructs. And there's also another class called prescriptive design rules, which are allowed patterns, that either are exceptions to otherwise defined restrictive design rules, or maybe a list of only allowed patterns, and the design can't contain anything else. And then separate to that, complementary, I guess you could say, is the application space of layout data mining and analytics. So this is using your pattern matching or pattern searching engine to analyze and extract information from a layout. The basic one is just pattern search. You define a pattern and ask your tool to go tell you where in the layout that pattern occurs. There's also pattern classification, which is sort of a meta analysis on top of that, where you're trying to find commonalities between patterns and separate or organize them into related classes. Pattern cataloging is kind of a newer technique where instead of the user defining a pattern and asking the pattern search engine to go find it, you sort of do the inverse operation and ask the tool to tell you what are all the unique patterns that exist in the layout. And then there's pattern scoring or all kinds of pattern analysis that you can do to further organize and filter the patterns that exist in the layout to maybe find out which are the most severe, if they're yield detractors, or all kinds of other metadata that you can attach to the patterns. And here's a couple of questions that came to my mind that I would be curious to hear answers to today. The first one is how can conventional design rule checking and pattern matching best be used in a complementary fashion? I think we've made a lot of progress in that direction as an EDA industry, but I'm not sure we've reached the kind of final evolution there. And how does the rule development methodology work between the two approaches? Is it are they so different that we need to do them separately? Does that rule definition, does it belong to the same team and the same skill set, or what should that look like? And then finally, I think a lot of the current DRC development process is still manual. Where you have in the worst case, I think, like Gyuszi said, you have one set of engineers that's kind of writing down or drawing pictures in PowerPoint or something, and then they hand that off to another team who tries to write it into a little more formalized design rule manual, and then you have another team that sits down and writes some code. So Opal would help you collapse a lot of that into one step, but you still need somebody that's writing the code. In an era where process technology is continuing to get more and more complex, the design rules, number of rules is expanding, and those rules are getting more complex. How long is that still sustainable, and how can Opal help in that respect? So I think with that, I'll turn it over to Luigi, or Maarten is up next. Okay.
Okay, so you're welcome. I'll first start repeating a little bit what has been said, introducing myself. Have been working on layout in various positions. First as a designer, struggling with rules, then at Segantec, doing compaction engines, so moving designs between one process and another process, so again seeing all kinds of rules. And finally at Takumi, trying to optimize layouts given a set of rules. And what it all came down to is, say also what Gyuszi said, is a struggle with design rules. What do they mean? What are they used for? How do I read them? They are ambiguous. I don't understand it. Can it be better? Can they be more aggressive? Hey, oops, this rule is missing. Design rule set fits are incomplete, etc. So that is my experience so far with design rules. And seeing that, we started Sage Design Automation and tried to get a solution around these design rules. So what we noticed is that there's a communication issue with design rules. They are not clearly defined. And if you have, say, a rule, if you have many rules, you cannot really design with those. So at Sage, we start with a clear definition of a design rule. Other than Gyuszi, we work with graphical drawings. That's at least for most of the rules. We try to make the representation as graphical as possible. And since there's, say, not a few rules, but thousands of rules, we are able to organize them into a full design rule manual. It's tables and many tables of rules with values, etc., layer definitions. And then finally, we verify what you have there. And you can read verify in many ways here. First, verify if the rule is right. Is the rule according to, say, the intent by the process engineer who wants to find a solution to some processing issue? So that process engineer can make the drawing which is on the left and then run the tool, do the online checking, and run that on the layout and check if the rule is indeed according to what he expects to see there, where it matches okay as green, where it matches and giving a failure as red. Verify is, of course, also when you are doing some design and, in initial stages of design, you are making a standard cell, your rules are, say, halfway done, before you have a sign-off deck, you want to try if the design is okay. So you run this rule set on your standard cell, and then you verify if the standard cell is right. Or also if the rule is right, say, can I design these cells with the given rules? And maybe we need a bit different trade-off between the rule and the layout. And then finally, verify, say, if your sign-off deck is right. So making out of the rules patterns which can be used to verify if the DRC deck you're writing or you have written, if that's correct or not. So this is what Sage do or what I do, and please be invited to have a look at the show, at the trade show here. So for today's discussion, I want to make clear a little bit, maybe it's not a hard line between, but what is the difference what we see as clip-based matching versus topology-based matching. With clip-based matching, people take a little piece of layout, often say like, say 100 or maybe up to a few hundred microns in the square, take that piece of layout and they want to find it on a full chip. So actually they search for occurrences of that layout on the whole chip. And Luigi will be able to tell you much more about that. But it's a well-defined process for if you're doing an exact match, and you can also have very dedicated algorithms for that, which do that very efficiently for large layouts, for large number of clips. And in ISI2, there's DRC Plus who does things like this. However, what we saw is that if some tolerance is applied to these layouts, then the definition becomes a little bit less clear. Say, you could say, I want to match a clip with, say, like 5 nanometer tolerance on each edge position. But what will happen if, say, like a little sliver outside the clip moves in? Does it still match that clip or not? And all those kinds of questions will be arising. So once you define some tolerance mechanism for these clips, it becomes unclear. And also, is say like, is clip A equal to clip B within some tolerance, and clip B is equal to clip C within some tolerance? Then is clip A equal to clip C? It's a question, say, it's a definition problem here. So these clips, it's in general good for hotspot finding. Say people see a problematic area of the chip, on the chip, and they want to find it on other locations. Now, if we go to the next matching process, we call that topology matching, and there you draw a topology, say polygons or partial polygons with relations between those, say like spaces, extents, overlaps, etc. And then on those distances you can define expressions, say this should be within some value or should be an exact value, etc. And then if that total set of topology and conditions on these expressions matches, you have found a match. And actually, this is very well suited for defining design rules. It's more work to do because you need to type all these expressions or enter all these expressions, but it's much more exact what's going on there. And it's also much more powerful because, say, we are not limited with this topology to a certain clip size. Say, like, there's nothing saying here that the clip should be 100 by 100 nanometers, but it could be a huge thing as well. So it's much more flexible. Now, what we at Sage do, we handle both, but I think today's discussion we will focus on the right-hand side, because that's also what matches with what Gyuszi is doing with fruit, or Opal best. That's close to what we call topology matching. So if I compare Opal, the Opal initiative, and ID Undress, there's some overlap, and we are trying to do the same. There's some differences, and I see ways where we can help each other, where we can improve. We are coming more from a graphical entry point where we say, okay, we must have a formal language where we describe the pattern we want to match, but instead of having the language as a focus like Gyuszi does, we have a graphical representation as a focus, and we both acknowledge that it must be formal, and because that's formal, you can drive an internal checker from that and do, say, what Gyuszi calls... Sorry?
And declarative.
It's declarative, yes. It's not imperative, it's declarative. And you can do the online checking or the immediate checking. Now, what we... and that's the difference. We see that people are struggling with languages. At least our target users, they want to see drawings, and we take these drawings as an input, and we can immediately take rules and run those rules, but we can also encapsulate them with a template, and that template can be used for some standardization where, say, like the simple rules, they are automatically done from a template, say like a simple space or a width. But if you have say like this difficult, logo rule, which is, say, probably hard to make a drawing picture of that, probably then a language could kick in, and then you could describe that with a language, and hopefully we can combine both mechanisms there. And if we look at a piece of our manual, it would be able to drive, say, like the fruit or the Opal checking, possibly our internal checker, of course, and then also third-party checkers. And maybe even routing tools or dummy field tools, as Gyuszi mentioned. Okay, thank you.
Very good. I just want to complement what has been said before, and actually taken from the introduction that Jason gave to look at what can we do after we represent our layout with a set of patterns. Patterns, either regular expressions, declarative regular expression, or topological expressions. I want to focus on the additional layer that we can build on top of our physical design and physical verification steps in order to understand better what we're actually building. One of the most difficult things to understand, a new concept, is what is the coverage, meaning what is the total set of patterns that actually match given design rules. Now, this concept can be actually formalized, and this is the novelty of thinking in terms of patterns, that if you just look at the design rules, maybe you understand only up to 15% of your physical design space. This is the space of all the possible things that your router, your custom layout, or any type of polygon pushing can generate. And I'm going to formalize it in a second. Then we build test chip expanding on layouts, and maybe we understand up to 50%. The reality is that when we build products, we go into fabrication without understanding up to 85% of the actual layout, which means that we have not simulated, we have not tested, we have not verified all the shapes that are actually end up on silicon. So how do we solve this problem? Well, first of all, we need to understand that this is a difficult problem. This is real data from chips that go out and are product chips that are made with 10 to the 10, 10 to the 11 patterns that are not in a test chip. So this is a real problem for founders. This is a real problem for actual physical designers as well. Because this is the first time you see this is on customer silicon. So how do we, and this actually was work that was shown a couple of years ago by Jason and AMD. So how do we go about understanding the coverage, which means the totality of patterns that can be generated? Well, it's a difficult problem. If we represent them as topologies, as Maarten has shown, or even as regular expressions, but with topology it's easier to understand the combinatorics around it. Well, if you look at all the possible matrices, this is a separating dimensions from topologies. This is 512 combinations. Of course, they're not all legal, they're not all physical, but even a subset is complicated. If you make a more complex pattern here, then you have a very, very large space, 10 to the 20, and actually in real cases, the space that we need to consider is 10 to the 60. So it's a very, very large space. Now, that's why you need to use advanced combinatorics and analytics in order to work on this. And it's actually possible to characterize this. First, you need to take all your topologies, understand all your distribution of your parametric variability, and then you can break down in components patterns. So this is, I want to say, although certainly fruit is a good start, I think it can be augmented with a topological representation that can actually consider the patterns that actually appear and also the patterns that do not appear, matching and not matching a certain regular expression or a certain topological matrix. And this is actually defining the full set. Coverage is the resulting set of all the things that appear and not appear in your design space. If you look at what has been done in the past, we have built databases of patterns, but if you actually use advanced combinatorics and analytics, you can actually understand all your patterns that are going to be designed, even the future ones that are going to be designed, from the very beginning, going from, the typical 2 to 3 years design and design and fabrication cycle, all to 6 months and understanding your entire physical space. Now, I just want to show you very quickly, this is not in the material that was distributed, the reason for understanding the coverage, the totality of your patterns, is that there is a structure to this space. There is actually an algebraic structure to this space which can be represented as a humongous graph. Okay, this is a slice of that graph in a high-dimensional space representing a full chip. What you see in the middle here is that the middle part is how many simple patterns occur, and the bubble represents the size of the patterns. As you grow out, the patterns become more and more complex, so they need to be represented with more pixels. Okay. Now, the good news is that in the physical design space, there is only a large but finite number of patterns that occur. And understanding and fully characterizing that means that we can actually build perfect test chips that contain all the distribution of patterns and parameters that we need. There is no need to randomly generate layouts anymore. We can understand exactly what needs to be put on a test chip. And furthermore, we can characterize products. Now, I just want to give you an example here using web searches instead of patterns to simplify. So if a pattern is a pattern, so it could be a set of words or a set of shapes, if I just search for a yellow shirt using a search engine, the web contains combination of words and text, for instance, in English or any other language, Hungarian or any other language, that can be tested. And they're the same size, more or less, of what a typical physical design is. So if I check for a yellow shirt, I get 575,000 results. You can try it out. That's the coverage for this combination of a yellow shirt. And then if I add more, a yellow shirt and blue pants, I get 66,000 results. You can see a trend here. As I add more bits, I get fewer and fewer hits. Okay, to the point that if I add a yellow shirt and blue pants with pizza, which is, of course, it's whimsical, but could be there. Who knows? Maybe somebody has written some interesting poetry. So you find 0 results. So there is a limit to the extension of your graph, and this is it. And furthermore, if you use the proper analytics, you can actually backtrack a little bit and say, where is my boundary? Where is the one hit if I actually subtract something? So if I take away width and I do an exact search, I found 1 result. And here, indeed, somebody robbed the Pizza Hut wearing yellow shirt and blue pants. Clearly not the smartest person, because, that's very I don't know. I would wear something else anyway, and I would not mug Pizza Hut. I don't recommend it. It's not good pizza. Anyway, sorry, but so. I'm going to end it here because I think we can have a very good discussion, but I just want to show you that you can represent combinatorially many, many different shapes all the way that it matters. This is a representation. This is what Jason was talking about, cataloging. You can actually get a catalog of your entire set of patterns that appear, and also the ones that do not appear in the design rules. Now, this is difficult to see. Just to give you an understanding, this is a very, very simple 4 bits. A via and a metal on top. You can have, intersection of partially enclosed vias, and even, inner corner for non-rectangular vias, and even, non-existent topologies here. So what you can do with this, you can actually look at how many patterns belong to layout A versus layout B. Very interesting. Also, you can see of something that, what is the dimensional distribution of the parameters in a pattern, and you can actually find out of 2 patterns what are dimensions in common also and dimension not in common, okay? So, and also you can do machine learning and predict hotspots, and I'll skip this part. I'll just leave you with a visual here. You can navigate this big graph and do prediction using machine learning techniques and even deep learning techniques, which we will present next year. Okay, this is it. Thank you very much.
Do it turn this mic so the audience can ask questions.
Oh, good luck, yes.
So this is the time where the audience can ask questions. We're going to turn this mic around. That way we'll be able to record your questions, and we're recording the answers. We will have a website with all this material up on the website, including the video. And last year we had like 10 times more people download that video than actually attend the conference, right? So attend the face-to-face session. So if you use the mic, then you'll get your questions. Please, when you ask your question, give your name and your affiliation, and then ask your question. You can ask it to any of the panelists or the entire panel. And that's about it. Do you have a volunteer for the first question, or should I ask it myself? Sometimes it just takes a little bit to get things going.
You got to use the mic then.
I'll use the mic then. So I guess this question is for Gyuszi. You've been doing this for a long time. When you do this, your fruit things, how do you think? Do you think in terms of relationships when you write your fruit code? Or do you draw a pattern and then look at that pattern and try and say, well, now how if I match these 2 things on this relative line and this up here? How do you, when you write your code, because you're about the only guy I know who is an expert on Opal right now, how do you do it? I mean, do you start out with like what Luigi is doing with like patterns and then drawing little things, or you start with your puzzle and put pieces together? How do you get yourself started writing fruit?
So can you hear me? The constraints come to me in English or drawing. So I do not come up with the constraints myself. So usually a different group comes up with the constraints, whether the constraints are process related or quality related or yield related or tribal knowledge related. So for example, when they create a cell or they wanna create a standard cell, they say, I want to have 3 hits on a pin of the cell, unless there's 2 of them in a line. But if there's a 4th one down there with 4, then it's okay to have 2, something like that. I do not come up with that. Somebody else comes up with that. Comes from tribal knowledge or somewhere, and I have to put that in some expression so that the tools can comprehend it. If it comes from process guys, they figure out based on their simulations or knowledge or years of experience, and they say, don't do this, or with the vias or with the wires, or do this, don't do that in English or drawings, and I have to take that and put it in some kind of formal mode, and now I put it in fruit. Did I answer your question, Jake?
Yes, thank you. So basically depends who's asking the question, the user or the process person, or maybe a verification
Correct.
person.
Correct. But I also can see that let's see, if I wanted to do a search in my database to find patterns that look like an airplane, now I could do it, right? In the past, it wasn't possible.
Rashid Topologlu, IBM. My question is for Gyuszi. So did you use this in a real product?
So we are using it internally. We have multiple tools, a lot of them which I've been involved with in the past. And we have some internal models for the tools, and we have converters from Opal to those models. And we also use the checker, the online checker that I mentioned.
So were they used in a real product?
Yes, yes. It has not taped out yet.
Hi guys, my name is Cyrus Tabry from ASML, and I think Gyuszi, you alluded to the constraint of designing this. Not all topologies or even bit combinations make sense in the extreme gridding we're going to. And Luigi, you referred to giant numbers. So how do we actually address the number of patterns that we need? You alluded to a problem of 10 to the 50 or 10 to the 70. I don't really know the difference between those two numbers, but
So well, I don't know. I don't want.
I think it's kind of for you, Luigi.
That's okay. The combinatorial problem is solvable. Okay. The good news is that the combinatorial problem is solvable in the sense that in order to search such a vast space, provided that that space is very sparse, okay, which is our case, okay. So just to give you real numbers, okay, we have seen more than 200 different full chips, and although it's still, you can say it's anecdotal, and it is possible that somebody is just going to go and generate a bunch of pixels, but most functional chips that are taped at all the technology nodes right now, the total number of patterns that represent, let's say, back-end layers, okay, are between 300,000 of unique patterns, okay, to 500,000 unique patterns, okay. So,
But what radius, right? I mean, how?
at any radius, from 1 pixel to the maximum pixels that you need to represent the entire complexity, which fits, let's say, 10 times in the optical radius or something. Okay. So
On the order of optical radius, I thought there'd be hundreds of billions of patterns.
No. Unique pattern. That is exactly what happens if you actually do the combinatorial analysis versus if you don't. The potential of the pixels, yes, there are. Just put a matrix. How many? If you take a matrix of pixels, But the question is, how many real patterns there are? How many words are in the English language, and how many words are possible in the English language, right? That is the difference. That is the difference. That is exactly the difference. And if you do, I'm just looking at the data. I'm not looking at the possible combination. And this is what I think we've been stuck for too long by looking at only the verification aspect instead of the construction aspect. Okay?
No. I mean, I'm thinking about the router. I guess, Jason, I thought when I read your papers, don't I see an order of billions by the time I get to significant radius?
So, I think in terms of the
Instances,
topologies,
yeah,
yes,
instances.
it's similar numbers to what Luigi saw. If you start adding in how many different instances where there's differences in the dimensions and stuff.
Unique patterns. It's less than 500,000.
It's less than a billion.
Less than 500,000.
Less than
I think-
500,000. Yeah.
Then I want to ask a question, say like, how do you define similarity of two patterns? Because if you have, say like...
The same as the representation is identical to what Sage uses, right? So it's the same. It's a topological representation with intervals and stuff.
Oh.
Yeah. That within that representation, you need to have the proper analytics engine and combinatorial. I read Jason's paper, and as I recall, Jason, since you're up there, I'll ask you. In your paper, you said that at 10 nanometers, you had around 200 billion possible patterns. And I think you said you had 200,000 unique patterns. Is that correct?
That sounds right. Yeah.
Okay.
Yeah.
Right. That is exactly what we're saying.
Okay.
The
so-
possibility, it's like how many words can you make with 26 words in the English alphabet versus how many words are used in the English alphabet and how many words, more importantly, are commonly used, which is an incredibly reduced subset, right?
Right.
And we still understand each other. I mean,
Right.
as engineers, we're capable of using possibly less than 1,000 words to express a lot of concepts.
Some even less than that.
Yeah, exactly. I mean, you know.
So we are making up new words every day too, right? I think that's part of the problem. We are making up new words. As new technology comes out, we have to come up with a new word to express that unique new technology thing. A good example is, I was told by Kleiner Perkins that today 2 billion photographs are uploaded every day to Snapchat or Twitter or Flickr or something like that. Whereas 5 years ago, it was like 10,000, right? So in a matter of just 5 years, we've gone from a few thousand uploads a day to 2 billion uploads a day of photographs. Well, as people see this tremendous explosion in pattern complexity, you have to focus in on what are you going to worry about. And your point would be, hey, we should worry about everything, but we should be very careful about the things we select to use out of everything we could use, correct?
Right. Yeah, there is the aspect of the finite and manageable amount of patterns, unique patterns that needs to be represented. There is also the aspect that even helps us, which is the combinatorial aspect, the fact that there are combinations of these patterns that need to be built up from the ground up all the way to the maximum complexity, which is then meaningful for lithography, for optical radius, but even for larger, for etch and larger length scales issues. So yes, and I just wanted to add this, to go to the field of machine vision. There are studies, there are articles that look at what is the complexity of patterns that our retina can actually understand. We can discriminate very easily using a small number of pixels. Okay, we do not need to store the full set of pixels that are in an image today. We don't have that capacity in our brains. It's more of a question of the graph that we can actually store, the representation.
Because they're looking for patterns naturally.
Yeah, absolutely. That's how we do it. And there are, there is an entire field of algebraic topology that is applied to that. Yes.
Thank you. My name is Biniam. I'm from Invensense. So I think if I'm getting what you're getting at, I've worked in a company previously that does DNA sequencing chips. And DNA, over 3 billion, what they're looking for is typically what causes cancer.
Mm-hmm.
So not the entire sequence, right? The sequence that causes cancer is what they usually look for.
Mm-hmm.
So that would be similar to what you were saying. You're only looking at what is of interest, not necessarily the entire combinations.
Right. Also, we analyze actually we have applications in the genomic field. That is,
Okay.
Yes, we read in the full human genome, right?
Yes.
But the thing, actually, I mean, this is well known. In fact, actually, this is a very welcome analogy that applies into, if you look at the way, the genomic field has been looking at combinations, right? You actually look at combination of the n-grams, 2, 3, 4, 5, etc. And then you get to a certain length where sequence starts to repeat and there are combinations of sequences, and then you're trying to find correlation with gene expressions, and from gene expression you go to actually cancer, and you need to find that. So the full sequence is still 3 billion long, but the combinatorial aspect of it allows you to treat it. You can look at. I mean, what is a gene? What is the maximum length of a gene, and also its combination of genes that are associated with certain pathologies. So yes, that's exactly how we do it. Yeah.
So finally, I mean, Opal just joined the SI2, right? Recently contributed.
Yes, we just contributed it last week.
So I think my question will apply to both three of you. So how has it been with the industry uptick in terms of the already existing EDA companies, mentoring, Cadence? Is there any interest from them to contribute more, or what has been the uptick?
I think that we'll see how it's gonna go. We don't know yet. There was interest, right? And we got questions and emails, but I don't think there was any action yet.
Yeah, if I look from our position, we see value here. It's partly complementary, and we, of course, we want to help the industry forward wherever we can. But of course, we also have our own focus on our solutions here. So we will cooperate when needed, and maybe also compete here and there.
We are planning on having a working group that will review the code and then could do code reviews of new code additions, and I'm fully committed to it. So this is pretty much my full-time job. I also want to mention that during layout creation, layout synthesis, there's many rules that come. They're not necessarily design rules or yield rules, but they are desires or quality rules. For example, if you do analog routing and you want to keep two wires next to each other, you have to express that somehow. And what happens if they have to deviate, and how do they deviate? Or if you have a cell level layout, there's all kinds of controls or constraints you have to put on the synthesis tools, right? And we found that having a language like Opal to communicate these desires is very good.
Yeah, I do have a slide on that, so maybe it's time to bring up Jerry. Jerry is going to be the program manager for Open Standards. Open Standards is one of our coalitions. Oh, is that what happened? I wonder what happened. Yeah, it didn't have any power. Okay. So yeah, I'm gonna bring up the next step slide since we're close to 1 o'clock. It's about that time.
So while they're doing that, Gyuszi, the airplane demonstration talks about how the cockpit is in a X position less than the wing.
Yes?
And then you flip the airplane over and say it matches.
So as I mentioned in one of my foils, the rule writer is supposed to write it only once, right? Left-sided, you write it the Republican way or the Democratic way, doesn't matter. And then the rule is supposed to flip, right? At matching time, you don't want to put the burden on the writer to write it both ways. If you don't want it to flip, you would say this is an unflippable rule or unmirrorable rule, right? Right now, the checker doesn't do it yet. But that's the plan to make it happen. I have another system prior to Opal which did the flipping, so I know how to do it.
Yeah, I figured that's where it had to go. Yeah.
So this answers the question from that was just asked. Here are the next steps. So we have the Open Standards Coalition that Jerry's the program manager for. That's what he looks like. Please see him if you would like to have more information about joining the Open Coalition, the Open Standards Coalition. The first thing I'm going to do is choose a chair and co-chair. Gyuszi will probably be one of those. It's my guess he would be. But we don't know who the co-chair was going to be. Then the chair, which will be those two people, shall prepare a detailed project proposal to submit the Open Standards TSG. So inside of the coalition Open Standards, there's a technical steering group made up of the members of, maybe you should tell us who's in there. IBM, why don't you come tell us about the Open Standards, who's in there and what will happen.
So the members of the TSG are those members that are both in Open Standards and our board of directors.
So at the moment, that's Intel, IBM, Cadence, Zukin, Qualcomm.
So we have a TSG of like 5 or 6 companies, right? So the chair prepares the project proposal, so we're big on projects, and so a project has to have deliverables, it's got to have goals, it's got to have, you know, the structure behind it, meetings, minutes, legal responsibilities, all that type of thing. Then after the TSG approves it, then we actually send it to our board of directors. And on that board, our next board meeting is October 5. At that board meeting, we'll make the go, no-go decision on actually launching this project. So that will happen on October 5, and then they'll approve the formation of the Opal working group. And then after that group has been launched, that'll be meeting weekly, and I'll be doing the program management for the weekly meetings. We'll have, they're usually done by WebEx or a teleconference or something like that. That will go on until the end of the year. What we'd like to do at SI2 is make deliverables every 6 months. So we start in, say, October, I would say by March of next year would be the first time. And we also like to demonstrate our progress at DAC. So probably DAC of next year, you'll see the first fruits of the working group. And also maybe by that time, Luigi will have his data analytics ready to demonstrate too.
Well, the demonstration is there, but we need to, as a startup, you know, we cannot afford to give it away for free to begin with. I mean, when we are Intel, yes, after we get to the phase of being Intel. After we buy Intel.
Okay, so that will happen later this year. So what that means is that we have some time for all of you, especially I see 4 or 5 of my mentor friends in the back seats back there, to think about this and to consider joining us. We really do want, I think somebody mentioned, we really do want EDA participation. We know what will happen if EDA companies don't participate. They'll not be adopted. So we want adoption. We're not into the science just for pure science. We want to actually solve problems. And to do that, it has to be in the hands of users who are using this new technology to solve their problems. So that's what we're going to do. So I want to thank our panel. I do have an Opal for each of you. And it's a nice Opal. I even bought a digital microscope so you could view it. But it got delivered 23 minutes after our office closed. So they're going to re-deliver it today. If you guys are here tomorrow, then I'll be able to give you your panel gift, right? So it's suitable to give to your wives or girlfriends or your dog. I don't care. Up to you. It's a nice pattern too. You'll find an Opal with a nice pattern in it. So let us thank our panel and close up. Thank you, everybody. Have a great day.